Now we're going to look at an old one, but a good one. 1995, question 10, part B. Okay, so this is a nice little one where we got force and air resistance. Not quite as horrific as other ones like 2009. So this is a good starter in this area. We know we have a particle of mass falling against air resistance. So the force upwards is mkv. And of course we know from before our force downwards is just mg. All right. It starts from rest, which is going to be important, and we have all those bits and pieces. So we need to prove in part 1, we're looking for the time is, when time is v is g over 2k, when the speed is g over 2k, the time is ln 2 over k. So we're relating, this was important, v and t. Okay, so therefore we're going to use the fact that a is dv dt. All right, now we know kind of where we're going. So let's figure out our forces. Our total forces on the object are mg minus mkv. And that is, of course, equal to ma. So if we just look at this part of the equation, we can cancel out the m's. And we know that our acceleration is g minus kv. So this is what we can work off, because that, of course, is dv dt. Now, I'm going to tidy up all these bits and pieces. So what we're going to do is we'll get our time over on this side and our velocities over on this side. So we know that there the dt is 1 over g minus kv dv. Okay, so to solve this little section of it here, okay, as we begin to integrate this, we need to know a little bit of integration by substitution. So in this video, I'm just going to give it to you. If you want to know how to actually carry that out, have a look at the video for 2009. So we can use the fact that the integration of 1 over g minus kv dv equals minus 1 over k natural log of g minus kv. All right, so that's our little factoid. And again, because integration by substitution is off the course, that's okay. You will get that in a question. You don't know how to do it, need to know how to do it. It's not that hard, but it's not for this video. So what we need to do on this one here is we're going to integrate these, and we're going to say that time, we'll look at our limits down in a second, is minus 1 over k, natural log of these guys, g minus kv, and we need to get our limits here. So what do we know? Well, it starts from rest. So at time 0, velocity is 0. It's always nice when they give that to us. All right, we're asked to prove the time is such and such a thing. So what I'm going to say is I'm going to let t be here, and at the end of this one, we're going to hopefully find t is the natural log of 2 over k. But we will put our value for v in here, which is g over 2k. All right, it's time to put all these bits in place. T minus 0, that's easy. Minus 1 over k, natural log of g minus k factor of g over 2k. A little bit ugly, but you can see this cancellation about to happen here, and it's going to get a bit nicer. Now, little place you can very easily make a mistake is you look at the 0 here and you go, oh yeah, grand, and we have minus 0. But not necessarily. So let's just write this one out here. So it's minus k, which of course plus 1 over k, natural log of g minus 0, so it's a natural log of g. Okay, so just be careful. It's very easy to drop that one out of there. So we'll tidy this up on the bottom line here. And we have minus 1 over k, natural log of, now these guys, we can cancel those two there. So it's going to be g minus g over 2 plus 1 over k, natural log of g. Okay, this is getting a bit better. You can see there's a little bit of tidying we can do on our next step. So let's bring it all up here. Now, time equals, to keep these tidy, I always like to put the positive term first and then the negative term, because then we can use our log relations. So we have 1 over k, natural log of g. We might just pull all the k's out together, minus natural log of, g minus g over 2 is fairly obviously g over 2. Right, got all our bits. So time then, of course, equals 1 over k, natural log of there we're going to go, we're going to have g minus g over 2. So it's going to be g over 2. All right. And that one we can cancel our g's. Just do straight away over here. 1 over, okay, the natural log of 1 over 2. And that, of course, is the natural log of 2. Put it all over k, just like we had in the question. And there we have it. QED. Okay, that's part 1. Now, that's not too bad. A little bit fiddly, but nothing too scary. So let's have a little look here at part 2. Now, for part 2, I'm going to give us a fresh sheet because there is a little bit of messing around in it. Okay, we need to show that the speed v goes towards g over k as t goes to infinity. All right, so again, I can see I need a v and a t kind of relationship here. So what have we got in the previous one that can help us out? Well, if we go back to this little section here, okay, we can see t is all of that. Now we've used our limit, so we actually really need to go back here and pop in a constant. So what we're going to say is, we're going to say that t is minus 1 over k, natural log of g minus kv. So we just double check that is just what we had here. Okay, there we are, and plus our constant. Now, I probably have an irrational dislike of constants, but sometimes they're quite easy to work with, and they really are if we get a v is t, v is 0 when t is 0. So straight away we can see 0 equals minus 1 over k, natural log of g plus 0 plus c, so c equals 1 over k, natural log of g. Well, that wasn't so bad. Okay, we can pop it out in a couple of lines. So now, let's go back and have a look at what we have here. We have t equals minus 1 over k, natural log of g minus kv, plus 1 over k, natural log of g. All right, so you can see the similarity to what we had before. Let's tidy this up because we basically want v on this side. So there's a little bit of working to get there. So that is going to equal 1 over k. I'll pull the 1 over k out just like I did the last time around. Natural log of g minus the natural log of g minus kv. At this stage you're getting kind of happy where it's going. 1 over k, natural log of g over g minus kv using our log relations. All right, this is getting a little bit easier to handle. So scoot the k over there because we're going to eventually flip into an exponential here. So what we're going to have is kt equals the natural log of g over g minus kv. Now, got to remember your little log relationships here. So if we have natural log of y equals x, what we're really saying is y equals e to the power of x. So that's your little bit of a relationship we need to know. Should be fairly comfortable with that at this stage. So what we're going to then say, we come all the way up here, is that g over g minus kv is e to the power of kt. Okay, so we're getting there, but there's still a little bit of ugliness to be had on this one. All right, let's begin to see, can we split it out? Because this term here has a v and something that's not a v. So we'll multiply this across. We have a g equals, I won't split it out in one go, that's what I'm kind of thinking, but it's always dangerous to have a little slip on that one. So g equals g e to the power of kt minus kv e to the power of kt. All right, this is the one I want on its own. I don't really want the minus, so I'm going to put this one over here and the g over there. So I get kv e to the power of kt equals g by e to the power of kt minus g. Getting better. So all I got to do is lose these different bits and pieces. I guess that's losing one by one. V is e to the kt is g by e to the kt all over k minus g over k. Now I'm going to simplify that a little bit and pull out the g and the k, because I can see that in my answer. G and k is kind of what we want out here. So now I just get e to the kt minus 1. All right, a little bit handier. Now we got to get rid of this troublesome e to the power of kt, because I want v equals something. Well, it's actually not as bad as it sounds, because it's g over k. Well, that divided by e to the kt is just 1, and that divided by e to the kt is 1 over e to the kt. Okay, now that's good enough. You can express this as well as e to the power of minus kt, but I'm going to leave it like this. It's a little bit easier to handle. Okay, so now what are we looking for? As time goes to infinity, what happens? Well, as time goes to infinity, e to the power of kt goes to infinity. Okay, and again, you can just, if you're ever unsure about this one, just take your calculator and kind of check it. I mean, e to the power of 2 is 7 and a bit. All right, e to the power of 20 is a lot more than 7 and a bit, and so on. So you can see it's going up and up and up. It's an exponential relationship. All right, so therefore, as t goes to infinity, 1 over e to the kt goes to 0. Because 1 over infinity goes to 0. So, therefore, what we'll find is that 1 minus 1 over e to the kt goes to, 1 minus 0, which is 1. So, therefore, as v goes to, goes to infinity, v tends towards g over k by 1 if you wanted, but g over k. So that is how we prove that. Nice little bit of a proof, not too bad. Bit of work getting used to these things, and once you're not afraid of the e to the kt, it looks messy as hell, but it's just normal algebra under it all, and pops out quite nicely.